Presenting Milestone 3 Accumulator-based vending machine. Prepared by Aidil, Mahfuzur, Naim, Hajidah, and Yusrael.
In this milestone project, a vending machine simulator illustrated in figure 3.1 was simulated. The major components used are adder, accumulator, night rider lights, prescaler, comparator, binary to BCD converter, input filter, and selector. The vending machine is based on a 4-bit accumulator, which keeps tracks of how much money has been deposited. The accumulator value equals multiples of 10 cents. It has two input buttons, button 1 for 20 cents and button 2 for 50 cents. Pressing a button adds 2 or 5 to the accumulator. The 7-segment display shows the current value of accumulator in BCD up to 15. When the accumulator contains 12 or more, the Night Rider LEDs will display one round of lights. We have prepared all modules of major components, simulated them independently, combined all the modules and simulated the combined version.
Adder.
For this part, the 4-bit ripple carry adder from milestone 1 can be used directly without modification, and no simulation is necessary for this circuit because it is completely reusable.
Here is the compilation report of ripple carry adder module. Accumulator.
Procedure from milestone 1 was used to build this accumulator. However, the function for this accumulator is different as the control line is called clear. One cell was built and simulated first, and followed by combining 4 cells to build the accumulator. Now here's the compilation report, schematic diagram, and simulation of the 4-cell accumulator.
This is the compilation report of 4-bit accumulator module. Based on the simulation waveform, the output of the pin Q is same with the input D, since the accumulator is functioned to store the value. So when the input is low, the output is also low, and vice versa. But when the clear is 1, it should not be storing any values and remain at 0. Night Rider light.
The Night Rider lights from milestone 2 can be reused. However, it runs forever. Having that said, a couple of modifications are required for this milestone project. The first modification is adding a control signal circuitry to enable and disable the lights, so that LEDs runs only when this input is high. The second modification is adding a status signal, done, that indicates when the lights have run a complete run. We have simulated this component to check whether if the circuit can be enabled or disabled on demand, and the done is activated at the correct time.
This is the compilation report of Night Rider module. This is the timing diagram simulation of Night Rider module. Based on the simulation waveform, when the last LED is lighted up, only the done output will give value high. So when the done is high, it will clear the value of at accumulator, and the accumulator will be 0, and the enable will be 0 again. Prescaler.
On to the next component, Prescaler. This component generates two outputs. The first is clock 1, a signal approximately 1 Hz. This speed is required so that the Night Rider light can run slowly and become visible to humans, whilst the second output is clock 2, a 100 Hz signal approximately. This speed is required to eliminate contact bounce that happens when a button is pressed. The Prescaler was implemented using a 26-bit up counter from LPM counter. Bit 25 was used as clock 1 and another bit was used as clock 2. The Prescaler was not simulated and it was not integrated with the main system yet, as it will be added to the final construction stage.
Here is the compilation report of Prescaler module. Iterative comparator.
This component gives a high output when the accumulator contains a value more than 11. We chose an iterative comparator from textbook in section 6.4, and these are the compilation reports, schematic diagrams, and simulation.
This is the compilation report of iterative comparator module. This is the timing diagram simulation of iterative comparator module. 4-bit comparator. This is the comparator schematic diagram. We first created the iterative comparator and it just compares 1-bit binary number. Then we inserted 4 of this iterative comparator in a circuit and cascaded them together to compare 4-bit binary numbers, which are A and B, while the output are E output and G output. The E output will be high when the value A and B is equal. The value of G output is high when A is greater than B. This is the compilation report of 4-bit comparator module. This is the timing diagram simulation of 4-bit comparator module. For the value A, it is inserted with value from 0 until 15 and B value is 1011 in binary. From 0 to 10, the outputs are 0 because A value is less than the B value. When A is 1011, which is equivalent to the B, then E output will be high and G output will be 0. After that, when the A value remains greater, which number 12, 13, 14, 15, and thus G output will be high. Comparator. This is the schematic diagram of the comparator used in binary to BCD converter module. This is the compilation report of comparator. This is the result displayed of timing diagram simulation of comparator. Conditional adder by 3. This is our schematic diagram of conditional adder by 3 module. This is the compilation report of conditional adder module. Binary to BCD converter.
The input to the converter is a binary input 0000 to 1111. The outputs are 7 lines to the tens digit and 1 line to the ones digit. Inside the converter, the binary input is first converted to BCD, producing a 2-digit BCD result using the conditional add by 3 adder module in section 6.2. A 7447 module turns the proper segments on the right hand LED display. No 7447 is necessary for the left-hand LED display because it is either turned off or displays the number 1. This is due to the range of numbers displayed is limited to 0 through 15. The tens digit is represented by D4, which can be either 0 or 1. D4 is connected to both segments B and C to display the number 1 when required.
This is the compilation report of binary to BCD converter. This is the timing diagram obtained from the simulation of binary to BCD converter. Input filter.
Button presses produce glitches that last to 1 to 10 milliseconds, which can be detected as multiple presses if a fast clock is used. A slow clock at the filter removes the glitches. The function of the input filter is to convert a button press into a single clean pulse. If the clock is too slow, the user must press the button for an unreasonable amount of time before the button press is detected. The frequency of clock input is not fixed, therefore it is changed to a more suitable frequency based on the switches used. We needed 2 copies of the filter, as in one for each button. The buttons are active low, which means that is high when it is not pressed. The input filter circuit produces a single pulse when high to low transition is detected at its input.
This is the compilation report of input filter module. This is the timing diagram simulation of input filter module. Selector.
The adder added the current value of the accumulator, which is the first input, and the value chosen by the selector circuit, which is the second input. The selector chooses a value to place at the second adder input based on this table. The selected value is presented for exactly 1 clock cycle for every button press.
This is the compilation report of selector module. When the button 2 is pressed, output while will give value 2, and button 5 is pressed. It gives value 5. At this moment, when both buttons are pressed simultaneously, it will give value 7. This is the timing diagram simulation of selector module. Accumulator-based vending machine. This is the schematic diagram of the complete circuit. However, with this circuit, it is unable to obtain a waveform and unable to simulate. Because in order to do that, we need the hardware for this circuit. Therefore, we are going to neglect the prescaler from this circuit. This is the compilation report for accumulator-based vending machine. Accumulator-based vending machine without prescaler. This is the schematic diagram of complete circuit without using prescaler. Based on the schematic diagram, the prescaler is removed in the complete circuit to ensure that the circuit can perform the waveform simulation. Previously in Milestone 2, we could not perform the waveform simulation with the use of prescaler because of the unavailability of the real hardware which is necessary for the circuit work. This is the compilation report for accumulator-based vending machine without prescaler. Finally, this is the timing diagram for accumulator-based vending machine without the prescaler. Thank you for watching.